roots as exponents? In this video, we'll derive a definition of roots as exponents and at the same time expand the definition of exponents to include fractions. We're going to translate expressions written as roots to those with exponents and vice versa.
Let's talk for just a minute about PEMDAS. Remember that PEMDAS is an acronym that helps you remember the order of operation. P stands for parentheses, E stands for exponents, multiplication and division are on the same level, and then finally addition and subtraction are the lowest priority operations, and they're at the same level. Now, the priority is based on the power of the operation. Addition is the lowest priority. It's kind of the weakest operation because multiplication is repeated addition. Exponents are repeated multiplication, so they come ahead of multiplication in the order of operations. And finally, the parentheses just act like an override mechanism in case we want to do one of the lower priority operations first. Now, the other thing to notice here is that operations at the same level are pretty much opposites of each other. Addition and subtraction are opposites. Multiplication and division are opposites. What's the opposite of exponents? Well, it's roots. So we need an R in our PEMDAS. Since roots are the opposite operation from exponents, they should be at the same level. Well, another thing to notice about these opposite operations is that they're really the same operation. Let me show you what I mean. A subtraction problem like 3 minus 2 can be rewritten as an addition problem, 3 plus negative 2. A division problem like 3 divided by 2 can be rewritten as a multiplication problem, 3 times 1/2. So in this sense, multiplication and division are really one operation. So then the question might occur to us, can roots be rewritten as exponents? And the answer is yes. We started with a definition of exponents where the exponent n counted the number of copies of the base x, and so n had to be a counting number. Then we derived some properties, and then we used one of the properties, the division property, to extend the definition of exponent so that it included both 0 and negative exponents. Well, if we want to write a root as an exponent, we need the exponent to do the job that the root does. Well, the job that the root does is taking an exponential expression, x to the n, and when we take the nth root of that expression, we get back to x, or x to the 1 power. If you think about the power to a power rule, it tells us that if we have x to the n and we raise it to the m power, we get x to the n times m. Well, if n times m wants to equal 1, then m should be 1 over n, because n times its reciprocal is 1. We can express the root as a fractional power. Now we have a definition of fractional exponents. So x to the 1 over n power is the same as the nth root of x, and in general, x to any fractional power m over n is the nth root of x to the m.
Notice that the numerator of the fraction m is the exponent of x, and the denominator n is the root. If I take 2 to the 6th power, 6 copies of 2 are multiplied. The result is 64. Now, if I write 64 to the 1/2 power, I can translate that as a square root of 64 and find out that the answer is 8. Or I can write 64 to the 1/2 power is the same as 2 to the 6 to the 1/2 power, which is 2 to the 3rd, and that's 8. So that gives us the same result with numbers, whether we write it as a root or as an exponent. 3 to the 5th power is 243. Now suppose I'd like to take 243 to the 2/5 power. One way to do that is to think of it as a 5th root of 243 squared. I can find that on my calculator. It's the 5th root of 59,049, and that turns out to be 9. If I rewrite it in an exponential form, 3 to the 5th power is 243, and that's to the 2/5 power. So that's going to give me 3 to the 5 times 2/5. The 5's cancel. 3 squared is 9. So this looks like a really good definition. It gives us the same answer no matter which way we think about it.